A block is sitting on an incline with an angle theta. The static friction between the incline and the block is mu s. Now we lift the incline so that its angle with the horizontal increases. What is the maximum angle, theta max, for the incline so that the block can still sit on the incline? So let's start by drawing a free body diagram of this incline. Trying to draw straight. So let's say that this is the incline and this is theta. So if this is our box, we're going to have the downward force of gravity pulling it down, the normal force acting perpendicular to the surface of the incline, and as well as the force of static friction keeping the box up. From this force of gravity, we can decompose it into a component parallel to the surface of the incline and one that's perpendicular to the surface of the incline. They form a right angle, and the angle theta is here. So using that, this becomes mg cosine theta, the vector that is perpendicular to the surface of the incline, and the force that is parallel to the surface of the incline becomes mg sine theta, using trigonometry. So now we have our free body diagram. We can start writing out equations. From this, we can say that the force of static friction, and I'm going to call this max since it is the maximum possible static friction that we're dealing with, minus a component of gravity parallel to the inclined surface, and that sine theta, in this case theta is the maximum possible angle, and that is going to equal the mass times acceleration, which is 0. The whole right side is 0 because there's no acceleration as the block is still sitting on the incline and you don't want it to slip. So from that, we can say that the maximum static friction is equal to the mass times the gravity times the sine of the maximum possible angle. And we also know that the maximum possible friction is equal to the coefficient of static friction times the normal force. And this is only true for the maximum static friction, as the static friction can vary in magnitude until it reaches the max, which is given by this expression here. Now we can use it in the vertical direction to solve for the normal force. So in the vertical direction, the normal force minus the component of gravity perpendicular to the incline must equal ma, which is 0, and it's sitting still. So the normal force is equal to mg times the cosine of the maximum possible angle. So now we can substitute that back in. The maximum static friction is equal to coefficient of static friction times mg cosine theta max. So now we have that. And now we can substitute this back into this equation here. So there's something that can be substituted back into there. So from that, you can say that the coefficient of static friction times mg sine theta max is equal to mg sine theta max. And this is from that equation by substituting the equation that we found for the maximum possible static friction. So I'm going to erase some of this stuff up here to make more room. Now, from this, we see that both of the mg's cancel, and we're left saying that the coefficient of static friction is equal to sine theta max divided by the cosine of theta max. which if you recognize this, you might recognize this as the tangent function of theta max. And now we're solving for theta max, so we just apply the inverse tangent function to the coefficient of static friction. And there's one thing about the coefficient of static friction, and it's that the maximum possible value of the coefficient of kinetic friction is 1. There's just no material with a coefficient of static friction that can be greater than 1. So this is essentially saying that the maximum angle is equal to the inverse tangent function of 1, which, if you remember, is 45 degrees. And so the maximum angle that this incline can rise to before the block starts to fall is 45 degrees. And that is how you would solve this problem here.